All right, in this video, we're going to learn a little bit about forces, what they are, how to calculate a net force, and how to draw a free body diagram. So forces are push or pulls that one object exerts on another. Metric force, the metric unit for force, is the Newton, named after Isaac Newton. In the English system, forces are measured in pounds. So everywhere we would use pounds in our day-to-day lives, you could use newtons if you wanted to be metric. But that doesn't usually happen. In metric countries, they tend to use kilograms instead of newtons. Newtons typically would show up in things like springs. You want to know how much force a spring produces, but if you're talking about going out and buying a bag of apples, newtons wouldn't be the unit. They would probably use kilograms instead. In the United States, we're stuck with pounds because there is no mass in the English system. So there's no differentiation for us. If you're talking about how much force a spring produces, it's going to be measured in pounds. If you're talking about buying a bag of apples, it'll be measured in pounds. We don't have that distinction. We don't have anything to use separately. A pound is roughly equal to 4.4 newtons. So a newton is a much smaller unit than what a pound is. And I tell you that to kind of set you up for calculations. When you're working with newtons, it's not uncommon to get rather large numbers. Now we talk about a person's weight. A person might weigh 130 pounds, and that's a number that sounds reasonable to us. But in newtons, that would be 572. So a number that we look at and go, wow, that can't be right, but it is. And the reason for it is because it's such a small unit. A newton is roughly equal to a quarter pound. So whatever you're thinking of in pounds, it would be about 4 times larger in newtons. There are 2 broad categories that all forces fall into. There are contact forces and there are field forces. Field forces are sometimes called non-contact forces. I like field better because it kind of describes what they are. They're those forces that are exerted with a field. Contact forces are ones that require contact between the 2 objects, thus the name. Field forces are those that do not require contact. The 2 objects do not actually have to touch for field forces to be exerted. And again, one of the reasons why they're sometimes called non-contact forces. Contact forces include normal force. This is one that you probably never talked about or heard of before. Normal force is the pushback from a surface that is opposing gravity. So as you sit there right now, you might have a computer sitting in front of you, and that computer is sitting on a table or a desk of some type. Well, gravity pulls down on that computer, and it's pretty normal for the table or desk to push back upward on that computer. It's that upward push that we refer to as the normal force. You may be sitting in a chair right now, and your body is pushing downward on the chair because of gravity. It's pretty normal for the chair to push back upward on you with a force that's equal in the opposite direction. It's that pushback. It's that reaction of the surface of the chair that we call the normal force. Again, called normal because it's pretty normal. That's what happens whenever something's resting on a surface. Applied force. This is the physical push or pull that is applied to a physical object or by a physical object. So if I were to push on the table to move it, I am applying a force to the table that is called the applied force. The computer is sitting on the desk. The computer is going to push downward on the desk. That's an applied force. Friction is the force that opposes motion when 2 surfaces rub together. Opposes just means it's in the opposite direction as the motion of the object. So if the object's moving to the right, then the friction is going to be to the left. Opposes just means in opposite direction. It is produced when surfaces rub together. That's because if you could look at surfaces on a microscopic level, you would see even the smoothest surface has contour to it. It's got little peaks and valleys in it. All surfaces have little peaks and valleys. And friction occurs when those little peaks and valleys get stuck in each other. So if I try to move this object to the left, the little valley and the top object would get caught by the peak in the bottom object. And it's that getting stuck, those peaks and valleys getting stuck in one another, that produces friction. Again, it's a force that opposes motion when surfaces rub together. Opposes means in opposite direction. Another contact force is tension. It's a pull applied by a rope or a chain attached to an object. So if I tie a rope to something, like a table, and I pull on that rope in order to pull the table, I'm really not producing an applied force on the table because I'm applying my force to the rope. What I'm going to do instead is have a tension force on the table. The rope is going to pull on the table, not me. So I refer to that force produced by the rope as tension. Spring force is a push or pull applied when a spring is attached to an object. If I take a spring and compress it, it's going to push back on the object. That pushing back on the object is called spring force. And we have air resistance. It's a special type of friction produced when an object moves through the air. As an object moves through the air, make me a little object here. Now let's say this object is moving to the right. It's going to have to take this air that's in front of it and move this air out of the way. It's going to have to take these particles and push them above, below, and around it. That takes force. That force is air resistance. When we get to the back of the object, those particles are going to want to get back to roughly where they were. So all those air particles are going to try to return and fill in the space behind the object. And it's going to produce a low pressure behind it because it's not going to be able to do it right away. There's going to be a gap here where you have partial vacuum. Ever held your hand outside a window, you can feel your hand being pushed back. But then when you stick your hand behind the rearview mirror, you don't feel that anymore. That's because you're sitting in that low pressure area where the air hasn't come back together again yet. That low pressure will actually suck backwards on the object, adding to the air resistance. It's a special type of friction. The object does have to come in contact with the air for it to be produced, so it is a contact force. Lift is another contact force. It's the upward push or pull exerted on an object as it travels through a fluid like air or water. It's produced by an object that has a curved surface on one side and a flat surface on the other. When you have air particles in front of that wing, those air particles will either split and go over the top of the wing to get to the back, or they'll go under the bottom of the wing to get to the back. They will make that journey in the same amount of time. So this particle going across the top will get to the back of the wing at the same time as the one going across the bottom. But the one that goes across the top, because it's a curved surface, has a greater distance to travel. Because it does a greater distance in a shorter amount of time, it has a higher velocity than the particles going across the bottom of the wing. It's this difference in velocity that produces the lift. When fluids move faster, the pressures drop. So you get a low pressure on the top of the wing that basically sucks it upward. That's how lift works. It's similar to air resistance, but air resistance is producing a force in the upward direction. This is called Bernoulli's principle, by the way. And then finally, buoyant force. Buoyant force is the upward force applied to an object by a fluid. So if I take something like a boat, and I stick it in water, the water is going to produce a buoyant force and push upward on the boat. The buoyant force is equal to the weight of the water that the boat displaces. So if the boat displaces 1,000 newtons of water, the upward force is going to be 1,000 newtons on it. As long as the buoyant force is greater than the weight of the boat floats. That's Archimedes' principle. Again, those are all contact forces. They require contact. A boat can't float in the water unless it's sitting in the water and pushing the water out of its way or displacing it. A wing can't produce lift unless it's coming in contact with the air to push some of that air over the top of the wing, push some of the air across the bottom. Applied forces can't happen unless the physical objects touch each other. Again, those are all contact forces because they require contact. The field forces, and there are only three, are electrical force, magnetic force, and gravitational force. These are the forces that have fields: electric fields, magnetic fields, gravitational fields. These are forces that all have fields. That's why I call them field forces. It's how they work. And a field is something that surrounds the object. This is what allows them to produce these forces without actually touching each other. So for example, if I have two balloons and I rub those two balloons in my hair, I will give both of those balloons a negative electrical charge. They will both have negative electrical fields around them. And then if I try to bring those balloons close to each other, they'll start to repel each other because of electrical force. They don't actually have to touch each other for that to happen. It's as they approach each other that will happen. It happens without contact because those balloons are surrounded by an electric field. And what we're dealing with is the interaction between those fields. I call it a field force. Same thing's true with magnets. If you take the north end of one magnet and the south end of another magnet, they'll attract each other. And they don't have to actually touch each other to get that attraction. You can feel the attraction as you move them closer and closer together. In fact, that attraction gets stronger and stronger as they get closer and closer together. That's because those magnets are surrounded by a field. And what you're feeling is the fields interacting with each other. They don't actually have to touch for the forces to interact. And gravitational. A bird flying in the air is experiencing a pull of gravity from the earth, even though the bird is not touching the earth. That is because the bird has a gravitational field and the earth has a gravitational field, and they will still interact with each other without that contact. And why I call it field forces. You'll notice I got little abbreviations for all of these. Normal force is F sub N. Applied force is F sub A. Friction is F sub F, and so on. Electrical F sub E. Gravitation F sub G. Because we're going to be drawing something called free body diagrams. A free body diagram isolates one object in a system, and it shows you all the forces that are acting on that object. We show those forces with vectors. We draw arrows. And oftentimes we want to label these arrows to indicate what forces they are. And we don't want to have to write air resistance, gravity, etc. We want to be able to abbreviate them, and that's what the FE, FM, F sub G, those are all about. Ways that we can draw these free body diagrams and show all the forces that are acting on them. Scientists are notoriously left-brain people, and because of that, they're not usually very good at drawing. So the good news is we don't actually have to draw objects. The object is shown as a box in a free body diagram. So if you ask me how do I draw a bicycle in a free body diagram, I draw a box. If you ask how I draw a person in a free body diagram, I draw a box. How do I draw a car in a free body diagram? Draw a box. You draw a box, and then you attach vectors to it, arrows, that point in the directions that the forces are acting on that object. Typically, again, label them to indicate what those forces are. Don't always draw the arrows to scale like we do when we're doing vector analysis, because we can actually write the numbers on those forces too and show what the actual number of newtons are. But sometimes they will be drawn to scale. You'll see short arrows for weak forces. You'll see longer arrows for stronger forces. When you draw free body diagrams, gravity is almost always involved, because the free body diagrams you're typically drawing are for objects on Earth. If an object's on Earth, gravity is one of the forces that you're going to have to draw on it, and gravity always goes down. Gravity always points towards the Earth, so gravity points down. And that's how down is defined. Down is the direction that gravity pulls. There will be something opposing gravity. Again, if you're on Earth, you're going to draw gravity downward, but there's always going to be something opposing gravity, something that is pushing up. That could be normal force, that could be lift, that could be buoyant force, that could be air resistance. So if I draw a free body diagram and one of my arrows on it is F sub G for gravity, I know automatically there is going to be an upward arrow for something else. If it's sitting on a surface, that is normal force. So if this object was a plant sitting on a shelf, gravity would pull down on the plant. The normal force from the shelf would pull up on the plant. So if it's sitting on a surface, it's normal force. If it's in the air, if it's falling, this is air resistance. Air resistance will be what pushes up on it. So when a skydiver jumps out of an airplane, gravity pulls down on the skydiver, air resistance pushes up. In fact, that's how parachutes work. When a skydiver deploys a parachute, it increases that upward pull of air resistance and actually slows the skydiver down. It's taking advantage of air resistance, the upward force opposing gravity. It could be lift if it's flying. So an airplane produces lift, helicopters produce lift. Buzz Lightyear does not produce lift. So remember, he's just falling with style. So it's just air resistance there. And if it's floating in water, it'll be buoyant force that is producing the upward resistance. So if it's a boat floating in the water, the upward force is buoyant force. If gravity is pulling down, something will be pushing up. And you always have that on Earth, always. Got some tips for dealing with motion. When objects are moving, their free body diagrams are more complicated. If it's moving, it's going to have friction, air resistance, or both opposing its motion. And opposing means opposite. So if I say I have an object and that object is moving to the left, I know going the opposite direction, I'm going to have friction. And if it's moving significantly fast enough, I'll have air resistance to deal with as well. Now this is if it is on a surface, the object would have to be on a surface for the friction to happen. Because friction is when the two surfaces rub together. So if this is a crate being pushed across the floor, friction's definitely there. Air resistance is negligible, so if you let air resistance off in a situation like that, it wouldn't be an issue. If we were talking about a car going down the road at 60 miles an hour, on the other hand, you've got friction there and you've got air resistance there because it's much more significant. In fact, the air resistance may actually even be larger than the friction is in an example like that. So opposing motion, friction, and air resistance. If it's in the air, forget the friction. If it's in the air, it's going to be air resistance and only air resistance. A good way to tell if you have friction or not is to look for the normal force. If you drew a normal force on your object, that means there is going to be friction there because it's actually normal forces that produce friction. So if you put F sub n, if you put normal force on your diagram, then the friction is going to be there. If you don't put normal force on the diagram, then it's not there. The last thing I have in here is about applied force, and applied force would be one that's in the same direction as the object that's moving. And I just wanted to point out to you and make sure you understood not all objects have applied forces. You can have something that's moving to the right, but there is no applied force on it. Think about hitting a hockey puck. Once that hockey puck is hit and moving across the ice, there's no more applied force. Once that stick and that puck are no longer in contact, applied force is done. It'll continue moving, but it won't have an applied force. So not always there. So let's just draw a couple just to make sure that we can do it. We got a lightsaber hanging on a wall. Well, we're going to assume this lightsaber is on Earth or some other planet, maybe Tatooine. So it's going to have a force of gravity acting on it. And force of gravity is F sub g. The force of gravity will pull downward on that lightsaber. Now, as we can see in the illustration here, this lightsaber is being supported by two brackets on the wall. Those brackets are counteracting gravity. Those brackets are producing upward forces to counteract gravity, and it's sitting on the surface of that bracket, so they are both normal force, F sub m. So we have one force of gravity, because there's only one Earth. We have two normal forces counteracting the gravity, one from each of these brackets that are holding it up. And that's it. Stationary objects are relatively easy to draw. Objects in motion, they have more arrows and they're a little bit more difficult to draw. So we have a wheel here that is moving to the right. That's what this arrow on the top indicates. This arrow is moving to the right. Again, we're going to assume it's on Earth. So there is a downward force of gravity acting on that wheel, F sub g. Wherever you have gravity, you have something that opposes gravity. This wheel is sitting on the ground. That is a surface. And the force that opposes gravity when something sits on a surface is normal force. The object is in motion to the right, and there are two forces that oppose motion. We are definitely going to have some friction here. That is F sub F. And it goes in the direction opposite motion. So since we're moving to the right, friction is going to be to the left. And depending on how fast that object is moving, there's going to be some air resistance pulling it backwards. If it's moving relatively slowly, that air resistance will be very small, maybe even negligible. But the faster it moves, the more significant that air resistance gets. There would be no applied force the way this picture is drawn. So that would be it. Those would be all the forces. For there to be an applied force, there would have had to have been somebody back here pushing on the wheel, applying a force to it to make it move. And if we had a person back there applying a force to it to make it move, then we could put this arrow up front for applied force, pointing in the same direction as the object's motion. But again, not every object in motion has an applied force. So you got to kind of be careful to analyze that situation. Here I have a ball suspended on a string from the ceiling, a pendulum that we can swing back and forth. Just to introduce something other than normal force, we're still going to have gravity pulling down on it. We're assuming it's on Earth. And that arrow is straight. There will be a force that opposes that, pulling upward on it. This is hanging from a rope or a chain. And that means that we're dealing with tension there. The ceiling is what's pulling it up and keeping it from falling, but the ceiling is not directly attached to the ball. If the ceiling were directly attached to the ball, then you'd call it an applied force. But since that force is being carried through a string, we would call it tension. And since this picture does not indicate any motion, there's no friction or air resistance to put in there. Don't overthink the free body diagrams. Now, the forces that are acting on the object are either balanced or unbalanced. Balanced forces are forces that are equal in size or magnitude and opposite in direction. Wherever you see the word magnitude is referring to the numerical value of that force, the number. It tells you how big or how small that force is. So for forces to be balanced, they have to be equal in size. The number has to be the same. And they have to be acting in the opposite direction. One to the left, the other to the right. One up, the other down. Unbalanced forces either have different magnitudes, they have different sizes, different numbers, or there's some direction other than opposite. They may be in the same direction, they may be perpendicular, but there's something other than opposite going on there. Those would be unbalanced forces. And again, they don't cancel out. Now, forces are vector quantities. Again, we just did free body diagrams and we drew arrows all around them. In physics, arrows are vectors. Forces are vector quantities. They have magnitude and direction. If the forces act in the same direction, you add them up. If they're opposite directions, you subtract them. You can also apply signs to the forces. You can say if a force acts to the right, it's positive. If it acts to the left, it's negative. If it acts upward, it's positive. If it acts downward, it's negative, and just add them together all the time. Either way works just fine. Do what you're more comfortable with. So here we have a free body diagram. And in this free body diagram, the forces are balanced. I have an upward force, which I can record as positive 2 newtons because up is positive. I have a 2 Newton downward force, which I can record as negative 2 newtons because down is negative. When I add them together, I get 0 newtons. They cancel out. Again, I could have also looked at that and said this 2 Newton force is upward, that 2 Newton force is downward. They're opposite directions, so I subtract them. And 2 minus 2 is 0 as well. They cancel out completely. There are actually forces on this object, but they act like there's no forces. This is Newton's first law we're going to learn. There are forces acting on the object, but those forces cancel out. They're what we call balanced forces. So this object acts like there are no forces acting on it. This is an example of unbalanced forces. I have an upward force of 2 newtons, which I can record as positive 2. I have a downward force of 3 newtons, which I can record as negative 3. Positive 2 plus negative 3 is negative 1. There's something left over. These forces don't cancel out. This object acts like there is a 1 Newton downward force acting on it. This is what we're going to learn to equate with Newton's second law. Whenever there is a net force, that's going to be the law that applies. There are 2 forces acting on this object, but it acts as if there's just that single 1 Newton force acting. A net force is the sum of all the forces acting on the object. You combine all the forces into a single vector. That is a net force. When we did vector analysis, we referred to that as a resultant. So net force is basically a resultant. If you have a complex free body diagram, you're going to have to simplify what you've got working on the object and then analyze from there. So all told, I have 6 forces acting on this object, 2 upward forces, a downward force, a force to the right, and 2 forces to the left. I have a total of 6 forces acting on this object. I'll need to analyze the vertical and the horizontal separate from each other and come up with a single vector for each. So in the vertical, I have a 2 Newton upward force, that is plus 2 newtons. I have a 3 Newton upward force, that is positive 3 newtons. I have a 4 Newton downward force, that is negative 4 newtons. Add all those together, I get positive 1. So I would have a 1 Newton upward force in the vertical. Then I analyze my horizontals. I have a 2 Newton force to the left, so that's negative 2 newtons. I have a 4 Newton force to the left, so that is negative 4 newtons. And I have a 2 Newton force to the right, that is a positive 2 Newton force. Add those all up, I get negative 4 newtons. So I have another component, the horizontal component would be negative 4 in that direction. So like I said, there's 2 things going on here now. We can narrow those 6 vectors down into 2 things, 2 different vectors. I've got a vertical vector of 1 Newton going up. And I have a vector to the left, ringing in at 4 newtons. So all 6 of those vectors that are acting on that object come down to or boil down to those two things, a 1 Newton up and a 4 Newton left. What I can do with that is a little mathematical analysis to figure out what the resultant is. And again, for mathematical analysis, I take my 2 vectors. Typically, I draw the horizontal one first, so I put the 4 Newton vector in, and then I'll put in my vertical one connecting it tip to tail. Tip of the first vector connects to the tail of the second, tip to tail. Make a right triangle with those. I will draw in that slanted resultant. That is the actual net force that's acting on this object, that black arrow. To figure out the magnitude of that net force, I'll use Pythagorean theorem. A squared plus b squared equals c squared. And it doesn't matter which one of these I call a or b. So I can do 1 squared plus 4 squared equals c squared, or 4 squared plus 1 squared equals c squared. It doesn't really matter. I went 1 then 4. 1 squared plus 4 squared is 17. That is c squared. To get down to the actual magnitude, I still have to square root it. So 4.1 newtons. 4.1 newtons is the actual magnitude of the net force. That's the strength of it. That's the number. Now it's a vector quantity, so I need to know the direction of this new vector. To get that, I'll have to find this angle right here. I'm going to have to find theta. And it's always the angle that's down at the origin of your drawing. If this was on a coordinate plane, the XY intercept would be right here. That would be the origin. And we always want to measure the angle nearest the origin, where we started our drawing, basically. So we need to know what this angle is here. For that, we do some trig. I always use sine because it's the first one in all the mnemonic devices, the easiest one for me to remember. Sine is opposite over hypotenuse. The opposite is the one that's not touching that angle, 1 Newton. The hypotenuse is the net, what we just calculated, 4.1. So 1 divided by 4.1 is 0.2439. To turn that into an angle, I'll do the inverse sine. The inverse sine of 0.2439. I'll punch into my calculator. And again, to do that, all you got to do is hit the shift or second function button and then the sine button, and that will give you the inverse sine. Put in that angle, hit equals, and you'll be good to go. So we know this is 14 degrees. Now you may leave it as 14 degrees. You may have to change it into a standard angle. All depends on what you're being asked to do and what level you're taking the class at. If you're asked for the standard angle, again, we need to remember that this right here is the origin, the XY intercept on a coordinate plane. And this is 180 degrees over here. And basically we are 14 degrees short of 180. So I do 180 minus 14 and I get 166 degrees. So depending on how you're being asked to do this, you may be good enough saying 4.1 newtons at 14 degrees, or you may have to give it as a standard angle and say that it's 4.1 newtons at 166 degrees. And we want to make sure we know exactly which direction that's going. In a CP class, we might be good enough saying that it's 14 degrees north of west, and that's good enough. In an AP class, you may be taking the AP exam and you're answers are all in standard angles, and you got to be able to figure out what the standard angle is to get the direction right. So again, it kind of depends on your situation. If you have an angled force like we do here, you have to break that angled force down into components, just like we did with vector analysis. We would start by drawing ourselves a triangle, the 7 Newton force at 40 degrees, the 7 Newton force at 40 degrees, pointing that down and left direction. And then I make a right triangle by connecting these secondary component vectors to it. And usually I'll draw the horizontal one first. So X is going over here to the left. And then I'll connect to the end of my net force or resultant with this Y component. And I got to figure out what X and Y are. It's going to be sine and cosine. Sine and cosine. Cosine will give you the adjacent side. So I want to know what X is. X is the adjacent side of this 40-degree angle. I'll use cosine to do it. It'll be cosine of the angle, 40 times 7, my hypotenuse. Cosine 40 times 7 is 5.4. So I know this up here is 5.4. To get this side over here, that is the opposite side. And whenever doing opposite side, we use sine. Because sine is opposite over hypotenuse. So sine of 40 times 7 will give us 4.5. So I know this side is 4.5 newtons. And again, what I've just done is I've broken those down into their component vectors. What each of the X and the Y parts would be. What arrows would it take to draw a 7 Newton force at 40 degrees? It would take a 5.4 to the left and a 4.5 down. So what I can do then is I can replace these, the 7 Newton 40 degrees, with those two new vectors. I can take this one out now. I don't need it anymore. And I can replace it with the 4.5 newtons to the left and the 4.5 newtons down. I said that backwards, a little dyslexic moment. 5.4 newtons to the left, 4.5 newtons down. And now once we reach this point, it's exactly the same as the previous problem. I need to get it down the two vectors and analyze it. In the vertical, I have 2 newtons up, that's plus 2. I have 4.5 down, that's negative 4.5. Add those together, I get negative 2.5 newtons. In the horizontal, I have 4.5 newtons, or 5.4 again, another dyslexic moment. 5.4 newtons to the left, so there it is. And I have 4.5 newtons down, which apparently 0.5 off. 5.4 minus 4.5 is 0.9. I'm gonna have to change the methods over here as well. Again, we've just eliminated the 4 vectors and just got ourselves down to 2. Negative 2.5 newtons means I'm going to have a downward one at 2.5. Negative 0.9 newtons means I'm going to have one to the left of 0.9. So again, I'm going to have to change this. All right. So again, the negative 2.5 newtons means down 2.5. The negative 0.9 means to the left 0.9. And again, I do my horizontal one in first. You don't have to. You'll get the same answer either way. I just usually draw the horizontal one first. To get the magnitude, we'll use Pythagorean theorem. A squared plus b squared equals c squared. And again, I'm going to change this one little thing. That's 0.9 squared. 0.9 squared plus 2.5 squared is 7.06. Again, that is c squared. We are going to have to square root that number to get the answer, and that is 2.7. So I know the magnitude of this is 2.7. That's the strength of it. The number part, that's magnitude. And again, you'll use Pythagorean theorem to find the magnitude. Now in either direction, we need to know what theta is. That's where the trig comes in. Trig is opposite over hypotenuse. And the good thing is the 2.5 was the correct number, so you don't have to change this one. 2.5 divided by 2 point, I do have to change it, 7. 2.5 was the right number. Hypotenuse is off because my original calculation was based on the number that used to be there. 2.5 divided by 2.7 is 0.9259. And then I do the inverse sine of 0.9259. And it's second function sine, and then that number, that is 67.8 degrees. We'll call it 68 degrees. Again, depending upon what level you're at, you might be okay to leave it at 68 degrees. Again, if you're working at a higher level, it might be based on a unit circle, to where this is a 180 over here. And we have gone 68 degrees beyond 180. And you would have to report that as 248 degrees. In a CP class, you might be able to say that you are 68 degrees south of west. And that might be fine. But again, if you're taking an AP class, your answer choices on the exam might be in a standard angle, in which case you have to recognize that this vector pointing this direction is pointing at 180, and you've gone 68 degrees beyond it. So 248 might be what you have to write down. Depends on the scenario, depends on the situation.